So today we're talking about the momentum and impulse theorem. Notice that we have the two letters J and P. So let's talk about that first. So impulse is going to be the letter J. Don't know why, it just is, accept it. And momentum, again, kind of a weird letter for it, is going to be a lowercase p. So when we say the JP theorem, we're just talking about the impulse momentum theorem. Okay, so first off, let's start off with momentum. What is momentum? Okay, so one way, an easy way to remember momentum, you can remember mass in motion. Okay, so anything that has a mass in kilograms and is traveling in motion, so has a velocity, meters per second, is going to have some kind of momentum. Okay, momentum is what makes an object kind of hard to stop. Like you have to stop a kid on a bicycle or stop like a moving semi truck, right? Because of the difference in masses and the difference in speeds there. All right. This conservation of momentum, don't worry about it so much right now. We're going to go into that next. All right, so our formula for momentum, just kind of like what we've written here, is just going to be that mass times velocity. So mass in kilograms times that velocity in meters per second. Okay, so our unit is going to be kilograms per meter per second. All right, so how do we relate this to kind of our prior knowledge? So Newton's second law states that in order for an object to accelerate, an unbalanced force must be applied. So net force equals mass times acceleration. You already know that acceleration is that change in velocity over time. So to change the momentum of an object, so in order to change the velocity, to have a change in velocity, to have a different final and initial, to keep it from going constant, you have to, and that's how you're going to change your momentum, you also must change it. Give me 1 second. I had it pulled up here. I want to make sure I copied the notes exactly. There you go. Must change its velocity, which is what I just said. I just wanted to make sure that that was it. Okay, must change its velocity. Therefore, momentum needs a force to be applied. Break it down to determine the formula we will use. F equals mass times acceleration, the one that we already know, right? If we break down acceleration, okay, then we get mass times that change in velocity over time, because remember, acceleration is just a change in velocity over time, okay? And we can even write that as final velocity minus initial velocity all over time, which is what you see here, okay? And if I was to break this down mathematically, do your distribution, you'll get mass times Vf minus mass times Vi over t, which remember that momentum is just mass times velocity, right? Mass times velocity. So what we're getting here is we're getting our final momentum minusing our initial momentum over time. So the change in momentum, in other words. All right, so that final momentum minus that initial momentum over time. And if we're talking for the change in something, we can write it as that change in momentum over time. Okay? Trying to make sure that I'm on screen with y'all. I need to make this like smaller here so I can see everything I'm doing. All right. Okay. So basically we're getting that the change in momentum over time, okay, and relating it to this force is equal to that, right? All right. So we're talking about impulse. Okay. So what is impulse exactly? It is the change in momentum of an object. So if you can change the momentum, normally with the force, right, in order to change the velocity, you're creating an impulse. And it's caused by a force exerted on the object over time. Okay, you can also say it occurs during collisions. Okay, we can talk about car crashes, we can talk about a racket hitting a tennis ball. There's so many different types of collisions. So two objects kind of are acting on each other. All right, our formula, make this small again. Sorry, I'm on my computer too. Make sure y'all can see everything I'm doing. Okay, our formulas, so we have two different formulas, right? So we just said that impulse is the change of momentum. So we have impulse is equal to the change of momentum. Okay, we also said that impulse is caused by a force acting over a period of time. Okay, those are going to be our two formulas. Okay, instead of having these written separately, we actually have a simplified, and it doesn't look simplified at the beginning, but once you learn how to use it and manipulate it, it actually does get more simple. All right, so J equals, we're going to combine these two, force times time, but we also know that J equals, okay, so if I'm talking about the change in momentum, it's going to be mass times that change in velocity. So if I'm given this final and this initial velocity, I can plug it in for that change in velocity, okay, which is also equal to that change in momentum. So I just kind of broke down this one into that. All right, so for example, so how this is going to work, okay? So example 1, a motorcycle with a weight of 882 newtons. So let's do our givens. I'm given a weight, force of gravity, Fg, of 882 newtons, is moving at 42 meters per second. Sorry, that's a velocity, 42 meters per second. That's going to be my initial velocity, my VI. If the motorcycle crashes into a wall and stops, okay, so that tells me my VF is going to be 0. And I'm given a time of 0.05 seconds. How much force acted on the motorcycle to bring it to a stop? All right, so one thing I want you to recognize is that this was the weight of the motorcycle, right? And we know that that force is acting in the down direction. We're not talking about the weight, and we're talking about what's bringing it to a stop, right? Okay, what force is bringing it to the stop is the force that's going to be acting in that horizontal direction, right? So what I can use with this, though, with my FG, I can use it, just like we did with force unit, to solve for my mass. So I'm going to take 882, solve for mass, 9.8. You can do a negative 9.8 there. It doesn't really matter because this would be negative, that would be negative. Cancel it out. Either way, you know mass can't be negative. 882 divided by 9.8, 90. So I also have a mass of 90 kilograms. So just another given thing that I know. And I'm not going to use that one anymore. All right, so I'm solving for force. So what I'm going to do, I'm going to look back up at this formula, right? So the first thing I want to know is what I'm solving for. I'm solving for force. So I look up here and I figure out which section has force in it. Well, it's going to be this section right here, right? So I'm going to bring this section down. Force times down. I'm going to put it on the left side of the equal sign because that's what I'm solving for. Okay, so then I'm looking at what else I'm given. I'm not given J. I'm not given impulse. Okay, but I am given, I solved for mass, and I have my change in velocities, right? So I'm going to go ahead and set it up to mass. And I'm going to go ahead and do it VF minus VI because I know the two separate numbers. You could go ahead and minus those ahead of time and plug them in if you wanted. Just going to write like this though. All right, so let's plug in what I know. So F I'm solving for, my time of 0.05, my mass of 90, final velocity of 0, initial velocity of 42. And let's plug in and see what we know here. So that's going to be 90 over potential 0 minus 42. That gives me a negative 3,780. Still have force 0.05. I'm going to divide by 0.05, by 0.05. Alright, I get a force of negative 75,600 newtons. That's our answer. Okay? So why is it negative? That's one of the questions. Okay? Well, it's negative because it's going to be decelerating. Kind of like working like friction does back in our forces unit, right? If this motorcycle is coming to a stop, it's opposing motion. So it has to be working in the opposite direction of the motion. That's why we get the negative. Okay? Back page. Alright, so real world applications. So which would be more painful? Okay, force applied to your hand, in other words. Catching a baseball stiff-armed or using soft hands? Well, more painful, definitely going to be stiff arm, right? Because you have no give. This is a lot like that rigid front frame that we talked about versus the crumple zone. All right, in the crumple zone, if you increase the time of the catch, if you have soft hands, instead of catching it like, directly, it'll be a give, so it's a slower catch. If you increase that time, in return, your force is going to decrease, which means less painful for the crumple zone, more painful for the stiff. All right, what are you changing by using soft hands? A lot of the time, I just thought of that and answered. Okay, time of impact. What is being held constant? The impulse. In other words, that change in momentum. Remember, both the balls start with same velocity, and both come to a stop in your hand. Sorry, my handwriting's not the best. What is changing? By changing that time, you're able to change that force. All right, if we wanted to prove like mathematically, we can throw some easy math in here, right? We're going to stick with the same formula that deals with force. That's what we want to know, right? And then we're going to do mass times the change in velocity. And we're going to do it again for a soft hand just to compare, right? So here, we're solving for force. Let's say we caught it in a time of 1 second using stiff arm, right? Really, really quick. Mass of the baseball was 1 kilogram, and it was going 1 meters per second and came to a stop. So the change of velocity is going to be 1 as well. Might be a -1, but it's okay for what we're doing right here. All right, so if I'm solving for force here, I get a force of 1 Newton felt on my hands. Okay, so let's do the same thing, but in this time, let's increase that time to 2 seconds. Mass still 1, change of velocity still 1. You get a force of 0.5 Newtons. So you can see with soft hands that you get less force because you increase that time. So if you increase time, you decrease the force. That's like our big picture, kind of what we're trying to do, right? And this is going to be indirect relationship. All right, so why are golfers told to follow through with their swing? Okay, well, if you follow through with something, you get to keep in contact longer, so you get to increase the time of contact, or you can say that impact again too, right? So sometimes we want to increase the time, but what's going to be remaining constant is going to be the force, right? Because a golfer is going to hit the ball the same amount of force that they can muster, right? Okay, so what's changing? Oh, sorry. So what are you changing by following through? Well, again, you're changing that time of impact. You're increasing it. Force is going to be held constant. So what we're going to end up seeing is that it's going to affect the velocity. This is why you follow through. You get a faster golf ball off that swing. Okay, so again, the math behind it, we're going to stick with the same formula. This time I'm going to go ahead and do, no, I'm going to do change in velocity, and that's just easier. And that's what it does in units. Yep. So this time, I'm solving for velocity. So I can muster 1 Newton of force. My half swing was only 1 second in contact. Golf ball has a mass of 1. Solving for change of velocity. That change in velocity, it speeds up 1 meter per second. Okay. Here, I still can only muster up 1 Newton of force, but this time I have contact for 2 seconds with that 1 kilogram golf ball. Now when I chop my velocity here, I get a change in velocity of 2 meters per second. So by holding that force for 1 more second in contact, right, I get to have double the speed. Okay, so if you increase the time you increase the change in momentum with that velocity of the ball. Kind of relationship, it is direct. Yep. Hope that helps.